So we need a smooth border, and also our sound does not always return back to the transducer, okay? Unless it's hitting at a perpendicular incidence. If it's going perpendicular to the source, then it's going to reflect directly back, just like a mirror. But if you stand in the mirror and stand cat a corner, you're not going to be able to see yourself. You're going to see whatever is at the same angle equal in the opposite direction.
That's what it means when it says slightly off the axis?
Absolutely.
Mm-hmm.
Absolutely. Okay. Any questions on specular reflection, guys? Specular? All right. Let's talk about our diffuse reflection, also known as backscatter. Okay. Backscatter is different to scattering in that backscatter and diffuse reflection is not chaotic. It's organized. It's not chaotic. Okay. And we get some of these signals back. So diffuse reflection, also known as backscatter, occurs when a boundary or interface is not smooth, and the wave reflects off an irregular surface and will radiate in more than one direction. Okay, so whatever the angle that it hits this, depending on the angle that it hits this irregular border, is going to reflect back in that angle. Okay, because if it comes down on a smooth border like this, if I hit this table, this is going to reflect back this way. But if this table like a mountainous or irregular, then it's going to reflect back in many directions. Okay. Again, that's figure 6.5 in your book. Okay. So diffuse reflection, also known as backscatter, the advantage is that surfaces at suboptimal angles to the sound beam still produce reflections and will return to the transducer. So even though it's irregular, we will get some of those reflections back to the transducer because they're going to come back at different angles. Okay. The disadvantage is that backscatter signals have lower strength than specular reflections. So that's going to require a higher degree of amplification when they come back. Right? So our diffuse reflection or scattering, right here, this is our irregular border right there. See, our sound is going to be reflected in multiple directions and it's going to come back weaker. All right? Just like right here. Sound coming down at an angle, again, like I said, the beam doesn't just shoot perpendicular. The beam is just going to come out and just be like, boom. The beam is going to change, it's going to shoot at this angle, it's going to shoot at this angle, it's going to shoot at this angle. Okay? I'm going to take all those reflections to create one image. Remember how fast sound is traveling that fast. So it doesn't look like all of that's happening in that time, but it is. Okay? So let's do a quick review on specular and diffuse reflection. These are quick facts. Okay? So specular reflection, this is stuff I want you guys to know basically about these right here. Specular reflection requires a smooth boundary. Okay? It only reflects in one direction. Okay? The initial angle is going to be equal to the reflected angle. All right? The reflections do not return to the transducer. Okay? It's organized, and always just think of a mirror when you think about specular reflection. All right? Diffuse reflection occurs with irregular boundaries, irregular borders. Okay, something that has an irregular border. Let me see. What has an irregular border? We look at a cirrhotic liver. A cirrhotic liver can be very nodular. You know how I can delete this, right? I can erase this, right? I'll just write over here. You know how the border of the liver should be like that, right? When you have cirrhosis, that's how the border of the liver appears. So it's not going to be a smooth boundary. Also, cirrhosis, because it appears to be, it appears nodular. You can almost see like it's mountainous. It doesn't look smooth, appearing like all of our livers look when we look at ourselves in the lab. Okay. So you will notice that cirrhotic liver is gonna produce a lot more diffuse reflection. Okay. That's not to say that we won't get an image still, but I'm just giving you an example of a part of anatomy that has an irregular border. Okay.
Diffuse reflection means because the reflection is going to scatter everywhere.
Absolutely. Backscatter. Okay, so this is my image again, guys. Specular reflection, reflecting in one direction. Diffuse reflection, irregular borders, reflecting in multiple angles or multiple directions. Okay. Smooth boundary for specular reflection, irregular boundary, diffuse reflection. Okay. Will not come back to the transducer. If our beam if our transducer is right here, this is gonna go the opposite way of the transducer. It's gonna miss the transducer. But some of these, depending on how it hits that irregular border, some of these will actually come back to the transducer. Okay? There's my example of that right there.
For the first image, it's also not go back to the transducer.
It won't. Specular reflection will not go back to the transducer. Okay? Again, this is our smooth border, right? Unless we're hitting something perpendicular to the beam, then yeah, it's gonna come right back to the transducer, just like the mirror. If I'm looking directly into the mirror, then yeah, I'm gonna see myself really nice, right? But if I change the angle of that mirror, then I'm not gonna see myself. I'm gonna see whatever's equal to the angle that I'm looking in the mirror at. Okay? That's the example of our specular reflection. Okay? So diffuse reflection, it needs irregular borders. You know, it's gonna scatter in multiple directions. Remember, diffuse also means backscatter. Scattering, guys. We're gonna finish scattering up and then I'm gonna let you guys go. You needed that? You got it?
It's not in the PowerPoint.
It's not. I just added this morning. So scattering, guys. Scattering of the ultrasound is the random redirection of sound in many directions. I know you're like, man, isn't that part of diffuse reflection? No, it's not, and I want to explain why it's different. Okay? So scattering occurs when the dimension of the boundary is small, that is equal or less than the wavelength of the incident beam. Again, that means it's going to be equal or less than 0.1 to 0.8 millimeters. Remember, we're talking about reflection. We're talking about something that's larger, much larger than the wavelength of the beam. Okay. So scattering is described as disorganized and chaotic. Okay. When we're talking about scattering, we think about the reason why we can't see the lungs, because ultrasound can't penetrate through air. What's happening? The reason you can't see it is because it's scattering. The sound is scattering. That's why you don't get an image. Okay. There's no sound being reflected back to the transducer. Okay, which would be the difference between backscatter, diffuse reflection, and scattering, period. Okay, because at least with backscatter, diffuse reflection, you're going to get sound coming back to the transducer. When you talk about scattering, you're not going to get any of that sound. It's going to just scatter and just be going in multiple directions except back to the transducer. You won't get any of those reflections back. Okay.
But the surface of the lung is so smooth.
I know, but the air, it's not about the air. It's not about the surface of the lung at that point, because the structure of the lung is going to be less than the wavelength of the incident beam. That's what it's about. The wavelength of the incident beam is going to determine, whether it's going to be reflect or whether it's going to scatter. Okay. Lung tissue scatters because the alveoli are filled with air. The alveoli in the lungs are filled with air. And again, we already know ultrasound can penetrate air. Okay? It can't travel in. Just think, if I had an ultrasound right now and I had it in the air, shouldn't I get an image? But we know it needs a medium to travel through. Right? Because as soon as it's coming out the transducer, it's just scattering everywhere, which is why we need gel on the patient so the ultrasound beam can transmit into the patient. That's why when you just put a transducer on the patient like this, that little air, that little space between the transducer and the patient, just that little bit of space is going to scatter that fast. Okay? That's why we need that gel, so we can have that as a coupling agent to reduce the impedance of that air. Okay? Higher frequency sound scatters more than lower frequency sound beams. We know that already, right? We kind of talked about that already.
Yeah.
Okay. So that's why, again, you can't visualize deep structures with a higher frequency transducer. All right. Scattering is directly related to the frequency. So that also means that scattering is directly related to attenuation, right? So that's just scattering in general. Let's talk about Rayleigh scattering or Rayleigh scattering. Rayleigh scattering is a special form of scattering that occurs when the structure dimensions are much smaller than the beam's wavelength. Okay? It redirects sound equally in all directions. Y'all have this, right? So that means when it hits something, when it scatters, that scatter is going to be scattering equally in all directions the same way. Okay?
That's what Rayleigh is?
Yeah, that's what Rayleigh is. Okay? This is described as organized and omnidirectional. Omnidirectional meaning equally in all directions. Okay? Red blood cell interactions with sound results in Rayleigh scattering. Okay? Rayleigh scattering increases dramatically with increasing frequency. So again, scattering is directly related to frequency. Okay? Rayleigh scattering is proportional to the frequency to the fourth of the frequency to the fourth power. Okay? That means when the frequency doubles, Rayleigh scattering is 16 times greater. We're good there?
Yep.
Okay. Oh. You get this? Okay. What is intensity proportional to? What is intensity proportional to?
Intensity?
Yes.
Oh, okay. Intensity. No.
Get with me later. That's your homework for tonight. That's your homework for tonight. An example of Rayleigh scattering would be when you drop a pebble into a pond and how those waves they start I don't know the word for it. They scatter equally in all directions. I like that. I like that. Omnidirectional in all directions. Figure 6-7 in your book. Okay? That would be an example of Rayleigh scattering right there. You drop a rock, boom, straight into the puddle. It's going to scatter equally in all directions out those waves.
Intensity, yeah.
All right? So let's do a quick review of reflection and scattering. So, specular and Rayleigh scattering, they're organized, right? Okay? So, and specular reflection will get some sound back to the transducer. Again, if it's perpendicular to the beam and the border is smooth, that's going to reflect directly back to the transducer. All right? Diffuse or backscatter is disorganized. Remember, it's disorganized, but that's also because our borders are irregular. We're also going to get some of that sound back to the transducer as well. Okay? When we talk about scattering in general, none of the scattering is going to be Rayleigh scattering or just regular scattering. Is going to get a reflection back to the transducer. All right. So Rayleigh scattering is considered organized. Remember, it's organized because it's going to be equal in all directions. Okay. And scattering, regular scattering, such as in the lungs, that's gonna be disorganized and chaotic. Okay. But with both scattering, sound is gonna go in all directions. Okay. And remember, Rayleigh scattering is proportional to the frequency to the fourth power. Okay. Rayleigh scattering is proportional to frequency to the fourth.
That's a given.
But then we say specular is not gonna go back or return to these.
Not all of it. Some of it, like I said, if we hit a structure with perpendicular incidence, this my beam, it hits this at this perfect angle, it's gonna go and come right back. If I hit this now at this angle, it's gonna hit it and go this way.
So it means where you hit it from the
Absolutely. From the incident angle. From the incident angle.
So what's the difference between diffuse and the scatter?
Diffuse and scatter is that diffuse or specular reflection is going to come back to the transducer. We're going to get a reflection back. scatter, we're not gonna get a reflection. Okay, the beam is just gonna scatter and go in multiple directions. Okay, so let's recall, guys. Reflection is likely to occur when the dimension of the boundary is large. We have a large boundary, such as the interface of the liver, the interface of the kidney. Okay, that is more than a few wavelengths of the sound. Okay, scattering occurs when the dimension of the boundary is small, that is equal or less than the wavelength of the incident sound beam. Okay, remember our typical values for wavelength in diagnostic ultrasound: 0.1 to 0.8 millimeters. All right. Rayleigh scattering occurs when structures' dimensions are much smaller than the beam's wavelength, so even smaller than what would be normal scattering. Okay. Higher frequency sound produces shorter pulses, which usually create more accurate images. Right. That's why we're kind of playing between frequency and depth, pretty much. Right. Depending on the depth we need, how deep we need to see in the body, we have to use the appropriate transducer according to that, or vice versa. All right. However, high frequency sound attenuates more and is less capable of traveling deeper depths. And I already explained why that's so. Okay. Thus, there's conflict between image accuracy and attenuation. Okay. The goal in imaging is to use the highest frequency that still provides the images to the depth of the structures of clinical interest. Like I just said. We understand this, guys? When? We're good? That wasn't so assuring, but all right. Okay. And I'll start on absorption.